Okay, so let's get started. So I'm delighted to welcome our first PRIISM seminar speaker of this academic year. Professor Amanda Luby is an assistant professor of statistics at Swarthmore College and holds a PhD from Carnegie Mellon University. Amanda's research is centered around developing statistically sound methodology to better understand individual differences in decision-making behavior, often using Bayesian tools. Dr. Luby currently works with the Center for Statistics and Applications in Forensic Evidence to improve the accuracy of analysis and interpretation of forensic evidence. And today, Professor Luby is going to talk to us about understanding human factors in forensic science using item response theory. So with that, Amanda, if you want to share your slides, I'll hand it over to you. Thanks.
Perfect. Well, thank you so much for the introduction, and thank you all for having me here today. Can everybody hear me okay and see my slides? Great. Always want to double check these days. Yeah, and so I'm very excited to be here today kind of talking about this research that I've been working on. This is some work that I started as a graduate student that I'm kind of continuing to develop and now work with undergraduate students at Swarthmore College. So I'm very excited to share it with you today. And so I guess I will start by just mentioning, I say forensic science, but forensic science really consists of many different scientific disciplines, and I like to think of them on this kind of subjectivity spectrum. So we have these disciplines that are very objective, so things like toxicology or drug analysis or single source DNA. And then on the other side of things, we have the very subjective disciplines, so things like bite marks and hair microscopy. And what I really focus on is what we call pattern evidence. And so these are things like bullets in firearms or fingerprints or tire impressions or markings produced when one object comes into contact with another object. This usually involves comparison of a crime scene sample to a known source sample. And so in all of these cases, we're really thinking about a forensic scientist looking at two samples and trying to decide whether or not they came from the same source. As you may have guessed from my title slide, my primary area that I work on is in fingerprint analysis. And so I think fingerprint analysis is really interesting to work on because it's one of those forensic science fields that we imagine to be very objective and automated. And, we see on CSI, these two fingerprints kind of popping up on a screen and a bunch of little dots and then a big, 100% match flashing. And in reality, it's a lot more subjective. And so really what is involved in this process does have some automation, does have some very fancy, computing and database searching. But at the end of the day, the 100% match is really up to an individual. So a forensic scientist kind of comparing a crime scene print to a reference sample and just trying to determine whether or not there's enough evidence there that they came from the same source. And so I also like to start off these talks just by mentioning the Brandon Mayfield case, because this was really like a catalyst to the work that I'm doing today. So in 2004, there was a train bombing at a Madrid train station, and there was a fingerprint found on a bag of explosives there. And so this was really like a huge international incident, a lot of news coverage. They didn't have a suspect. And so the Spanish police sent out this fingerprint to a lot of different international agencies and kind of said, look, if you can search this through your database and see if you come up with a match, that would be really useful. And so one of the agencies that they sent this to is the FBI, and the FBI came back and said, good news, we found a 100% match in our database. We have the person. But the person that they found, whose name is Brandon Mayfield, was a lawyer in Portland, Oregon, had an expired passport, hadn't left the country in 10 years. And there was kind of some other sort of additional information about types of cases that he had worked on as a lawyer that maybe had flagged him. And obviously this wasn't the person whose fingerprint it was an Algerian national that they later found. But Brandon Mayfield, was sent to prison for a while. And in, these anti-terrorism laws in post 9/11, there really wasn't a lot of recourse for him to challenge any of that. And so, he was detained for months before he was let go. And so this again turned into a big news story, really bad press for the FBI and for forensic science as a whole. It was, really controversial at the time. And so this led to a National Academies report that was published in 2009. And so I just have a couple of highlights that I'll share with you. And so this report was really designed to sort of gauge what the state of forensic science is in the United States. And so one of the things that they found is that in the US, the threshold for making a source identification is deliberately kept subjective. Another kind of soundbite is that the outcome of a fingerprint analysis is not necessarily repeatable from examiner to examiner. And I just want to pause for a second. Not necessarily repeatable from examiner to examiner. And so whether or not a person is found to have committed a crime or not could depend on the fingerprint analyst who is seeing that crime scene evidence. And then finally, one of their calls to action was that the accuracy of pattern evidence analysis needs to be evaluated in well-designed and rigorously conducted studies. I guess I'll also just mention here, because I think it's kind of a fun little tie, is that my first grad school advisor, Steve Feinberg, was one of the reviewers for this report. And so, that is one of the things that kind of kicked off statisticians being involved in forensic science. And so after this National Academies report came out, one of the things the FBI did was design an error rate study. And so the goal of the study was to estimate casework error rates, kind of how many false positives or false negatives do we expect in practice. And so this was done in 2011. There were 169 participants. These were practicing latent fingerprint examiners. It wasn't a random sample. They just recruited everybody that they could who, did fingerprint analysis as part of their job. There were 744 items. Each item was a one-to-one comparison, so one crime scene print and one reference print. And the other thing I want to mention is that this is one of the first studies where the fingerprints came from known sources. So there had been error rate studies done in the past, but they had used fingerprints collected at crime scenes, and so there's really no ground truth there. And so here we actually had ground truth in the prints, which seems like something that would be common practice, but really wasn't at the time. Each examiner who participated in the study saw roughly 100 questions. They were given several weeks to complete the exam, and test conditions were not controlled. And so I think for people who have worked in testing in other settings, this is kind of surprising, right? Because some people did this while they were at work and were paid for it. Other people did it in their downtime at home. People might have started a question and then walked away and then came back to it. They could have worked together. We just really have no idea. And so the two kind of main results that I'll start by highlighting. So first is the false positive rate. And so false positive is an examiner making an individualization or an identification. And so they're concluding that the prints came from the same source when they actually came from different sources. And so we care about these types of errors in practice because these are what can lead innocent suspects to being prosecuted. And so the false positive rate that they found in this study was 0.1%. So 1/10 of 1%, which is very small. But I also want to point out that it's not zero, right? So there are false positives. They're very rare. And so that's what they found in the study. The other type of error that they measured was a false negative. And so these are exclusions when prints actually came from the same source. So the examiners concluding that the prints came from different sources when really they came from the same person. And in the real world, we care about these types of errors because these types of errors can lead to guilty perpetrators going free. So they actually have the correct person, but they exclude them, and so they're not further investigated or prosecuted. And so this error rate was much higher in the study, 7.5%. And I think this was a little surprising to people. And so one thing, one kind of problem with the study that people have proposed is that maybe examiners, when they were doing this study, were more cautious. After that 2009 National Academies report, maybe they really didn't want to make false positive errors, and so they made more false negative errors and fewer false positive errors than they would in practice. And so I'm a statistician. A lot of us are statisticians here, and so a natural kind of next step that we might think about is, okay, those are the overall error rates, but what about the variability in those error rates? So here I have each person who participated in the study as a dot, And people who made false positive errors are highlighted in green, everybody else is in purple. And so we can see that the most common score is 100%. So most people who participated, or the most common score was 100% out of all the people who participated. And then we can also see that some people made quite a few errors. So in the 70 to 80% range in terms of percent correct. And also we can see that, there's very few false positive errors kind of sprinkled in there.
One quick question, Amanda, just from the chat. Somebody asks, Robert Pickett asks, are fingerprint analyses in actual practice usually one-to-one, or is it one-to-many, like comparing a single print against a database of prints?
Yeah, this is a great question. And I think both happen in practice. Sometimes in investigations, they will have a suspect in mind. And so that would be a one-to-one comparison. But if they don't have a suspect in mind and do a database search, then it might be, 1 to 10 or 1 to 20. And so it all kind of depends. I think both are common in practice, but one-to-one is easier to measure. And so I think that's kind of why they focused on the one-to-one comparisons in this study. Great question. I guess I'll also mention that even if it is a one-to-many comparison, usually what examiners will do is do many one-to-one comparisons. And so it's not picking out which print is most likely to be the source of the print, but are they the source or are they not the source, if that kind of makes sense. Great. So kind of bumping back to these percent correct. So one of the things we might say is, okay, this gives us a sense of what that variability is like. Most people are pretty good. These people are pretty bad. But these people over here might say, well, this isn't really a fair comparison because the people who got 100% saw easier prints than I did. And maybe I just got unlucky in the subset of prints that I saw and got a lot of very messy, kind of hard to analyze prints. And so this is where item response theory comes in. And so I have a one-slide introduction to item response theory for you. So these types of statistical models are used in educational testing when students sit for different versions of the same exam. So if you think about the SAT or the ACT, there are many that's given every year. We want scores to be comparable regardless of which year or which version of the exam students took it. And so we have to make some adjustments based on the difficulty of the questions that they see in that particular version of that exam. And so the way that we will go about this is modeling the probability of a correct response based on participant proficiency, which we call theta, and item difficulty, which we call B. And so this is nice because we have our participant proficiency, we have our item difficulty, and so we can account for people seeing different subsets of questions based on the difficulty of the subset of items that they saw. And so throughout this talk, I use a very simple item response theory model, which is called the Roche model, which if you've seen logistic regression, this is just a logistic regression where we give each person a parameter and each item a parameter. And then our goal is to kind of estimate those. And so what this probability curve looks like, is our kind of usual logistic curve. So here's just a kind of a reference point. So if we have a difficulty of 0, this line kind of represents the probability of getting that question right, depending on your proficiency. So as your proficiency gets higher, you're more likely to get that question correct. And if your proficiency is exactly equal to that difficulty, you have a 50-50 shot of getting the question right. If we have an easier item, those are negative difficulty values. And we can see that you need a lower proficiency to start to increase your probability of getting that question right. And if we have a more difficult question, so a more positive B value, then you need a higher proficiency in order to start increasing your probability of getting that question right. Great. And so another thing that I do in my work is I often use a Bayesian approach to estimation. And this is for a variety of different reasons. I think one of the most important is that in the context of these forensic studies that I look at, there's a large variation in the number of observations per item. So there's a lot of missing values, and the missing values are kind of not completely missing at random. And so I think Bayesian methods, when we have that kind of prior distribution, are able to account for that difference in n's per item a little bit more easily. It also gives us a way to estimate the posteriors for proficiency and item parameters simultaneously, and we get these nice uncertainty around those parameters kind of for free. It also gives us a natural hierarchical framework for more complicated models, which I'll get to later in the talk. And then I use the STAN estimation framework and have a bunch of code available on GitHub, and please feel free to reach out if you want to talk more about that. I use some pretty standard priors, mostly normal priors, pretty flat, and then I try to estimate the covariances or variances in this case when I can, rather than setting them. Great. And so if we look at the results from fitting this Roche model to this black box study data, we can see that our proficiency estimates correlate with the observed score while accounting for the difficulty of items. And so here I have the observed score on the x-axis, the proficiency estimate on the y-axis, and so we see there's this nice increasing trend. So people who are more likely to have a high observed score are also more likely to have high proficiencies and vice versa. But where IRT is really helpful, so in purple I've highlighted, I think there's 11 people here who received between a 94 and a 96% in terms of the observed score. And so really, if we're just looking at the percent correct, they're not really distinguishable from each other because they're all kind of tightly clustered in that small range. But if we look at that subset of people, but now the x-axis is their average question difficulty. So we just take their subset of items and calculate the average difficulty of those questions. It's maybe a little bit hard to see because our sample is pretty small here, but it does increase as we kind of move up. And so people who see more difficult questions on average tend to receive higher proficiency estimates. Those who see easier sets of questions tend to receive lower proficiency estimates. And another nice thing about this is I've also colored the points here by the percent that examiner was conclusive. And so one of the reasons that we see such a variation here is that some examiners are inconclusive very often. And so those values are just missing in this framework. And so what I think is nice about these IRT results is that it kind of implicitly accounts for that. So I didn't do anything special, but we can see that when examiners are conclusive more often, they also tend to get the higher proficiency estimates. And so I think that this is great. Is this the end? We've only been here for 17 minutes. No, it is not the end. And so I really want to take the rest of the time today to kind of talk about some complications and some of the things we've been working on to account for these kind of more complex problems than just looking at error rates. And so the three that I want to spend some time today talking about is first accounting for a sequential decision process. So in fingerprint analysis, we call this ACE, so analysis, comparison, and evaluation. I'll also talk a little bit about secondary responses. And so these are things like difficulty or response time or confidence. And so it's another response that depends on proficiency and item difficulty, but is separate from the actual final decision that they made. And then lastly, I'm really excited to talk about a little bit of kind of current work that I'm thinking about on minutia markup in fingerprint world. Great. So I will start it off with the sequential decision process. And so I think we'll walk through kind of what one of these questions in the black box study looked like. So the first thing that examiners saw was just a crime scene print. So a latent print, it's kind of messy, it's kind of blurry, it may be partial or not. And so here examiners were asked, does this have value for source decision, or does it have no value for source decision? So if it's an extremely low quality print, they can say this has no value, there's no point moving on. And so if they said that, then the question was done, and then they went to the next question. If they said that the print had value, then they would see the reference print next to it. And so you can see that it's much easier to see the detail in this print. It's kind of taken under ideal conditions. It should be complete. And so then they looked at these two prints side by side and could make an individualization. So saying the prints came from the same source, an exclusion. So saying the prints came from different sources, or they could say inconclusive. So there's not enough information to tell either way. And then also, if they didn't make an identification, they were also asked to report a reason. So if they made an exclusion, the possible options were pattern. And so this is kind of like the overall ridge flow that you see in the fingerprint. And so if those don't match, then the prints are from different sources, or they could say minutia. And so these are kind of like the smaller details in the print. So when the ridges kind of come together or go apart or end. So that was the other reason that they could mark. And then also for the inconclusives, I've kind of grouped them into these two categories, either close inconclusives. And so this was, there is corresponding information between the two prints, but not to the extent needed to make an individualization. So I kind of interpret that as leaning towards a match, but there's not quite enough information there. And then the other two are no overlap. So there's no overlapping area between the two prints, or just a kind of catch-all insufficient information in the print. And so throughout the rest of this analysis, I kind of group those two no overlap and insufficient information together as one kind of inconclusive category. And then finally, they reported the difficulty of the question on a 5-point scale, which I will get to in a few minutes. And so if we look at the distributions of the number of inconclusive and no value decisions that each examiner makes, so again, now each of these points are examiners again. They show up in both of these dot plots. There's a huge amount of variability. So some examiners almost never make inconclusives, and some examiners made almost 50. So this is almost half of the questions that they saw, they said it was inconclusive. And same thing for no value. Some examiners are much less likely to make no value decisions, and some examiners are much more likely to make no value decisions. And so this is something that we want to capture in our analysis. And so I didn't make it super explicit in the first part of this talk, but in the original IRT analysis that I did, all of these responses were just missing. And so they weren't correct and they weren't incorrect. They just weren't there at all. And so if we start to think about, how do we incorporate those inconclusive and no value decisions into our analysis, the first thing I thought about was, okay, let's just make a more complicated scoring method. So in the previous analysis that I showed you, they were just treated as missing at random. And so this is how they calculated those casework error rates. And so it's nice because it corresponds to the original analysis that was done. But we end up ignoring over 30% of the responses. And so that's, from a statistics perspective, we're just throwing out a lot of data. And so we don't really want to do that. We could also treat the inconclusives as incorrect. And so this will penalize examiners who are inconclusive very often. But this may actually be the correct response for low quality prints. And so some examiners may be penalized when we don't want them to be penalized. We could also treat them as partial credit. So there's a class of IRT models called partial credit models. And so this is nice because it distinguishes between errors and inconclusives. But again, it still doesn't account for when an inconclusive should actually be the correct response. And every time I've given this talk, especially to forensic science audiences, I get, well, what if you scored it this way, or what if you scored it that way? So we could think about using consensus answers for an item. We could think about using the best answer. So if any examiner was able to make a conclusive decision and it was correct, then everything else is incorrect. The list kind of goes on and on. Everybody kind of has their own opinion on what should be incorrect and what should be correct, and kind of how we could go about scoring this. I'm not a forensic scientist, and so I don't really want to be putting, my biases into this analysis and kind of making that decision on what's correct and what's incorrect. And so I accidentally hit the back button, and so I'll just go through that again really fast. And so what I kind of landed on doing was this IRTrees framework of Debach and Parchev, which I think is a very clever name for a statistical method. And so the basic idea is that we use a decision tree. So we kind of construct a decision tree, and then we will fit a Roche model at each node of that decision tree. And so for every single item, we first ask, was it no value or did it have value? And that gets a Roche model. We then ask, okay, was it excluded based on pattern? So is it very obvious that they came from different sources or not? And that gets a Roche model. The third node I kind of think of them as the match branch. And so is it more likely to be a match, or is it more likely to be a non-match? If it's in that match branch, was it conclusive? So was it an individualization, or was it a close inconclusive? And then same thing on the non-match branch. Was it conclusive? So did the examiner make an exclusion based on minutia, or was it inconclusive? And so in order to model the responses, we can just kind of multiply our way down the tree. So the probability of a close inconclusive is the probability that y1 is 0, y2 is 0, y3 is 1, and y4 is 0. Great. And so this results in a lot of parameters. So for every examiner, we have 5 parameters, and for every item, we have 5 parameters. And so this kind of results in a lot of latent variables to look at. And I guess really quickly, I'll just mention that I also use a Bayesian framework to estimate this model, again, really relying on normal distributions and trying to use a lot of Stan's recommended priors to make this run as fast as possible. And so we end up with a lot of parameters. And so I think it's really helpful to kind of compare these to a quantity that we can kind of think about in the observed responses. So on the x-axis here, I have the percent correct again. So just, from the original analysis, if they made errors or didn't make errors. And then on the y-axis, we have the theta estimates for each node in the tree. And so in this first panel, we have that no value tendency. So examiners that are more positive are more likely to make no values, and examiners that are more negative are less likely to make no values. And so as percent correct increases, examiners are more likely to make no values. And so this might seem a little weird at first, but it actually makes a lot of sense, because if examiners are saying that a lot of prints have no value, then that means that they're sort of getting rid of a lot of the low quality prints at an early stage. And so there's not really a chance to make an error because they're reporting those no values earlier in the process. And here is that same kind of trend, percent correct compared to theta for every single branch in the tree. And so none of these relationships are extremely strong. It's maybe most strong in the exclusion tendency. So examiners who are less likely to make exclusions tend to get higher percent corrects. And so again, that's because of this kind of artificial how we scored the data. Examiners who are inconclusive more often would have more missingness in their responses that doesn't go into the calculation for percent correct. And then, so the only other thing I want to mention here is in this theta 1 and theta 4, so tendency to make no values and tendency to make individualizations, that's where we see estimates that are furthest away from 0. And so when estimates are far away from 0, that means that there's kind of more variability there. Those decisions are driven more by the examiner than by the item. And then similarly, theta 3, so that kind of match or non-match branch, are actually pretty close to 0 on average. And so when I initially started thinking about proficiency, I really thought, a natural way to think about it is how good are examiners at distinguishing non-matches from matches? And that's actually where we see the least amount of variation. And so this is kind of a good trend. Yeah, so I just got a question in the chat about compared to false positive rates as opposed to percent correct or another measure of accuracy. I'll point in my references to an online textbook where I kind of played around with different measures of percent correct. And depending on how you kind of define accuracy, you can find trends with these different theta estimates. So if you think about how likely someone is conclusive, that's going to correlate with theta 2, theta 4, and theta 5, kind of where we bin those responses in the tree. And the thing that I'll mention about false positive rates is that there were so few false positives in this data set that for whenever I look at that, it's just a few points kind of scattered around and then everything else at 0% false positives. So great question. Great. And so the thing that I really want to emphasize about this approach is that I find it really useful for comparing examiner behavior in a more fine-grained way. And so here I have the theta estimates for 2 examiners. Both did not make any errors on the original test, so they would have that 100% percent correct. But if we're just doing the percent correct analysis, we really wouldn't be able to tell a difference between these 2 examiners at all, right? They're performing exactly the same. But if we dive into their IR tree estimates in a little more detail, we can see that examiner 3 is, the examiner in purple is more likely to make no value decisions, less likely to make individualizations, and less likely to make minutia exclusions. And so they're throwing out more bad latent prints, and they are not coming to a conclusive decision as often as other people. And so kind of in a practical sense, that examiner is performing worse than examiner 95, who's more likely to make individualization decisions and more likely to make exclusion decisions and less likely to make no value decisions. And so examiner 95, in terms of like information we can get out of the crime scene prints that we get, is doing better. And so this is where I think that this IR tree approach is really useful, kind of thinking about places where we can see differences in examiner behavior that may not result in like a difference in the final decision that they're making, but could improve casework in practice. I think this is also just kind of a nice way to think about, or a nice place to kind of think about what would be ideal. And so in a perfect world, all of these estimates would be 0, right? All examiners would be making the same decisions on every single print. All of the differences in decisions would be totally driven by the item and not driven by the examiner estimates at all. And so that's just kind of another frame of reference that I kind of like to keep in mind. Great, and so that is how I've kind of approached these sequential decision-making processes. The next kind of human factor that I want to talk about is incorporating a second response into these models. And so this is kind of going back to that last piece of the black box study that I skipped over. So the difficulty of the question on a 5-point scale. And so after examiners kind of went through each question, they were asked to rate that the difficulty of the comparison on this 5-point scale. And so what I've done here is use a joint model for both responses. So if we remember our Roche model for each node in the tree, this is a logistic model that depends on an examiner estimate and an item estimate. There's an extra index here, K, and so that just indexes which node of the tree that we're in. And so to model the reported difficulty kind of within this IR tree framework that I just talked about, we use a ordered logistic model for the reported difficulty. And so there's a ton of parameters here, but I will walk you through them. So the first thing that we include in this model is the IR tree propensity at branch K. And so we want to kind of capture if the reported difficulty is already captured by the latent variables that we used for the responses. We want to be able to include that in the model. We also add this participant reporting bias. So HI, it's indexed by the same index as the thetas. And then also an item reporting bias. And so this would kind of capture if there is something about the item that is making people report it to be more difficult that's maybe not captured in their responses. And then we also include a scaling factor. So just to make sure that because we're using this ordered model, making sure that we're able to get any flips in signs and kind of incorporate that. And so really what I'm going to focus on is talking through this participant reporting bias. And so if we look at those H's kind of compared to that same percent correct that we've been looking at throughout the talk, it's not really related at all. So people who are more likely to overestimate difficulty have higher H's. Folks who are more likely to underestimate difficulty have more negative H's. And we can see that doesn't really correlate with percent correct, either under the original scoring or in a scoring method using the IR tree scoring, and so kind of a consensus-based scoring approach. And we can also look at that reporting tendency compared to each of the thetas that we get from the tree. So again, above 0 means more likely to overestimate difficulty. Below 0 means more likely to underestimate difficulty. And again, we're not seeing a ton of strong relationships here. Maybe a little bit in theta 4 and theta 5, so those individualization or exclusion tendencies. People who are more likely to make those conclusive decisions are maybe more likely to underestimate difficulty. And so that's a little bit interesting, but I was kind of surprised not to see a strong relationship here between these decisions. And so one thing I want to mention is that using these raw responses, using those reported difficulties may lead to overfitting. So they did a retest where they had the examiners who participated in the black box study re-answer 25 questions that they had seen in a previous study, but 9 months later. And so here I have for you kind of a comparison in the initial black box study compared to the retest study, and the percentage of time that each examiner used the obvious reported difficulty, so the easiest possible response. And so there's a lot of line crossing, and so this isn't really a stable measure. There's a lot of intra-examiner inconsistencies here. And so I actually think that really designing a model to perform well on this reported difficulty may just be overfitting and kind of fitting to noise, since these reported difficulties aren't really a consistent measure. And so one of the things, I'm kind of skipping to the second bullet point here, one of the things that I've started to work on with a Swarthmore undergraduate is using a rescaled difficulty. So rather than having 5 categories, what if we just have 3 categories? So kind of difficult, average, or easy. And is that maybe a little bit more consistent? And also thinking about kind of in a perfect world, if we could run more studies, it would be nice to have a non-subjective secondary response. So something like response time or eye tracking that doesn't really depend on an examiner's, kind of individual reporting system, something that they don't really have a subjective control over. And then you may be wondering kind of why I'm even thinking about this. So some countries, not the US, but some countries in Europe have moved to a subjective probabilistic reporting system. So something like examiners, rather than saying this is a match or is not a match, they might say something like, based on my previous experience, I think there's a 99% chance that these came from the same sources. And so if examiners are if they have differences in their reporting styles, this is something that could have downstream effects, and we really want to be able to capture and measure. And then in my last kind of 5-ish minutes, I want to spend some time talking about what I'm currently looking at, which is minutia markup. And so what I mean by minutia markup is this process when examiners are looking at a fingerprint and kind of trying to get the information out of it. What they're looking for largely is these, changes in the ridge pattern. So are the ridges coming together? Are they splitting apart? Are they just ending? Kind of what are like the weird little details in this print? And these historically have formed the basis for uniqueness in fingerprints. So kind of going back to, 1800, I actually don't know when the first fingerprint was used in court. This feels like something I should maybe know, but these minutia have really formed the basis for uniqueness historically. And I think this is kind of interesting that the original matching algorithms, so kind of the computer systems that are used to do like database searches or just kind of make an estimate for whether prints came from the same source or not, were designed to mimic that human decision-making process. And so a lot of the kind of early algorithms that we see had a lot more to do with like minutia detection and kind of, rescaling the X and Y axes to like try to make minutia match up on different prints, rather than doing the more kind of black box computing algorithms that are used a lot more often for image analysis now. And so even now, when we have these kind of more sophisticated algorithms to do image searching, examiners can mark minutia fingerprints into the identification systems or not. And so some of these database search systems, examiners can say, there's a minutia here, there's a minutia here, and here, and here, and here, and then pass that in. Or they can just pass the raw fingerprint in, and it can kind of do that automatic minutia detection. And so if there's kind of variability in how examiners are marking those minutias, this could have massive downstream effects, right? We don't really know how these systems use marked minutia in coming up with their list of potential candidates, because this is really understudied, and we don't really have a great sense of how variable these minutia markings are. And so there was a follow-up study to the black box study. So if the black box study was treating examiners as black box decision makers and just trying to get at that casework error rate at the very end. The white box study was designed to let people look into the box that is examiner decision making and try to see what they're using to come to those decisions. So in the analysis stage, which is kind of looking at just the latent print on its own, they marked the clarity, so kind of the image quality of the print, and then they marked the features, and then they also go to the comparison and evaluation stage and do the same thing for the reference print. And so this is, in terms of the information that we have, a much richer study, because for every single item that every single examiner item pair in the data set, we not only have their final decisions, but we also have where they were marking these clarity features on the latent print. We have where they marked the minutia for the latent print and the reference print, and then also that final decision that they came to. And so I will very quickly just talk about two kind of projects. So the first thing that we're thinking about is, okay, can we separate examiner effects from print effects if we're looking at those minutia markings? So here is a single latent print. Each examiner who saw that print kind of has a different color. And so we can see that there are some, clusters of minutia that are very clear. People are probably finding the same minutia. But we can see this purple examiner over here is marking a lot of minutia that other people didn't see. And there's not really a lot of blue or purple points up here. And so there's a lot of variability in how examiners are marking. And so a natural question we might ask is, how can we separate the strong examiners in marking these minutia from the weaker examiners? But in order to do something IRT-like, we must first construct a response matrix. So what is correct and what is incorrect? And there's really no way to tell if a minutia marking is correct here or not. So we don't have access to the prints kind of for privacy reasons. So all we have are those XY locations of marked minutia. And so one of the things we're looking at is this two-stage clustering approach. So first we will cluster the minutia markings on a fingerprint, and then we will construct a response matrix that has a 1 if the examiner did mark a point in that cluster and a 0 if they didn't mark a point in that cluster. And there's some challenges here compared to a usual statistical approach to doing clustering, because we don't want geographically far minutia in a cluster, even if the algorithms kind of feel like they should be together. And we also don't want points marked by the same examiner in a cluster. So if the same examiner is making 2 points, even if those points are right next to each other, we don't want those to be in the same cluster, because if a single examiner marked them as separate, they should be treated as separate minutia. And then also, we need to find something that's really efficient. So IRT is already fairly time consuming to estimate. And now we're talking about many fingerprints in the data set, kind of doing these 2 stages on every single fingerprint. And so we want to come up with something that is efficient. And so this is something that I'm working with a student at Swarthmore who is thinking about grad school and would be a great candidate. Another thing that I've started to look at with some students is when examiners are moving where they're marking the minutia. So we have a Shiny app here if you want to kind of explore the data a little bit yourself. So here are 2 latent prints where the minutia was marked by the same examiner. And so these are 2 of the same latent prints. On the left, it showed up in a non-matching pair, and on the right, it showed up in a matching pair. And this is the same examiner marking the same print, but in these 2 different questions. And so whenever you see a line on the right here, that means that the examiner moved where they marked the minutia from the analysis to the comparison stage. So before seeing the reference print and then after seeing the reference print. And so when it's shown in a non-matching pair, they're not making any movement. So if it's a non-match, they're not kind of trying to force their minutia markings to match any reference print. But if they're trying to make a match, then they are moving minutia between those 2 stages kind of after seeing the reference print. And so this is something we're calling imputation, because they initially didn't see anything there. After seeing the reference print, then they might see something there. And so this is something that we're trying to start to look at and quantify and kind of dive into a little bit more, because I think this is a really interesting aspect of how the different stages of a fingerprint analysis are not well defined, and oftentimes examiners will kind of go through them circularly. And that is most of what I have. So just extremely quickly to summarize, I think the main takeaway is that IRT really provides more information than traditional percent correct scoring and has a lot of potential in forensic science, not just in fingerprint examination, but kind of any discipline that relies somewhere on subjective human decision making. Modeling the larger decision-making process rather than just the end correct or incorrect tells us where that variability is most likely to occur and kind of allows us to start thinking about how we can improve our training programs to minimize that variability. Differences in how difficult items are reported to be, as we found, is largely unrelated to their source decisions, which I think is quite interesting. And also variability in minutia markup has these downstream impacts, but hasn't really been given much attention. And so this is something that I'm really excited to be working on and hope to, have something to share in the near future. And then the other thing I want to mention is that there were a couple times, both in reported difficulty and in this minutia markup, where we have this intra-examiner variation. And so within examiners, these decisions aren't even necessarily consistent. And so I think this is also something that we have to account for when we think about, proficiency testing and error rates and casework and even how examiners are testifying in court about their results. So thank you so much for your time. I have some references here if you're interested in diving in more. I also just want to really quickly acknowledge CSAFE, who funds a lot of this research and also has a ton of projects kind of across forensic science in the statistical realm. And so I highly recommend going to our website if you're interested in learning more about other projects that we have. So thank you so much for your time.
Thank you so much for that great talk. I'll kind of clap on behalf of everybody. So let's open it up for questions, and it looks like there's a couple in the chat. So maybe we can start with Jay. I guess Jay, if you want to unmute and ask your question, and just before I do, I'll just make one plug, which is that for the students on this call, you should also just feel free to ask questions and to speak up as well. But with that, I'll turn it over to Jay.
Okay, I first saw you. Oops, sorry, my internet's a little laggy. I first saw your prior version of this talk at IMPS last year. God, I lose track of time. But anyway, I was very, very, very interested, and I really think overall the IR-Trees approach that you take is very much the future of this kind of categorical data analysis, and thoroughly hope that a number of the older models like the graded response model disappear because they make no sense. So I just want to make that plug. But I really think that, have you thought about trying to apply some of these to other kinds of subjective assessment processes, which are typically modeled quite poorly? So other example would be like free responses, essays, clinical assessments, where there's often like a sequence of gate questions or a decision made by the doctor and then some follow-ups or things like that. So I think the overall approach is actually much broader than just forensic science.
Yeah, I totally agree. And I think that, forensic science is kind of this weird place to kind of focus on. But I think you're exactly right that these clinical assessments are maybe somewhere that is most like forensic science. So I've been thinking a little bit about like radiology. So, reading an X-ray, and that kind of has this similarity to the minutia marking because we have these like X and Y coordinates. I think there's also a lot of issues in these subjective measures of quality, in some sort of sample that may be coming into. I'm not super familiar with a lot of these, data collection process, but I think anywhere where there's this element of like proficiency testing or, performance of a decision maker that is a more complicated decision-making process than just like correct or incorrect. I totally agree with what you're saying.
But as I said, I really, to me, this is like one of the really first great examples of the use of the IR-Trees type approach to solve a real problem. And I think, like I said, I think I really hope it replaces the older models, which don't make much sense. I mean, they just don't, they don't really make a lot of sense. The only other thing I would mention is the subjective probability very much reminds me of prior elicitation. And one of the things we know is experts tend to be overconfident. Like grossly, sometimes grossly overconfident. So it's, yeah. All right.
Yeah, well, so there's this other kind of interesting thread of people who have been doing research on different ways of communicating a probabilistic, likelihood that the prints came from the same source. So is it a likelihood ratio? Is it a probability? Is it, a 1 in 10,000? And running some surveys to look at, in I think they call them mock jurors. How do these mock jurors interpret those different different ways of expressing the same probability? And that also has a lot of variability in it. So I think that, yeah, it's going to be a really hard problem if we ever get there in the US.
Probably not. But the only thing I'll say is I'd like to get in touch with you because I want to offer you a speaker slot in my department if I could do that.
Oh, great. Yeah, that would be lovely.
Great. So let's move on to the next question in the chat by Robert Pickett. So Robert says, I'm curious how you're thinking about the implications of this research. Sorry, I guess I should have given Robert you the opportunity to read your question yourself, but since I started, I'm just going to continue. Is the goal to have estimates of reviewer performance or details of the print pattern to present at trial for context for the finding, or is the goal to make fingerprint matching analysis better? What does better fingerprint matching look like? How should we balance false positives and negatives? And of course, Robert, feel free to unmute yourself and add anything.
Yeah, so I'll just go ahead and get started answering this question. I think that, my particular goals are really more on the training side. So I think that, so in practice in forensic science, examiners have to participate in annual proficiency testing, but those proficiency tests are very easy. And so there's almost no mistakes made on any question in any year on those proficiency tests. And so really what I'm kind of trying to advocate for is we should be giving harder proficiency tests, but also we can adjust those scores to kind of make sure that examiners aren't penalized if they get, this hard, a hard question on a particular exam. Because I think there's this kind of sense in the community that if a proficiency test has a hard question on it, then like they're trying to be tricked, and that it's not really fair for them to, have to answer that question, since a lot of the responses that they make on those proficiency tests are actually discoverable in court. And so I think for me, I'm really focusing on ways that we can improve the training process, and kind of thinking, really early on, and also very separate from casework. But I think, down the road, hopefully we would see some of these effects in, standardizing the way that conclusions are reported, standardizing the training, standardizing, how inconclusives are treated. That is also like this extremely controversial question in forensic science: is are inconclusives an incorrect response in any cases? And so I think that, that's really what I'm thinking about. Does that answer your question?
It does, yeah. Thanks so much.
Great, thanks.
Okay, we probably have time for maybe one or two more questions. So I'll just open it up. Feel free to ask anything. Otherwise, I have a lot of questions, so. Now's your chance. Okay, well, I'll ask one of mine then, since I'm here. So I was wondering, and I think you sort of alluded to this a little bit when you were talking about the minutia markup, but like, I'm just wondering what the role is of sort of automated like image matching techniques, right? I mean, I'm reminded in all this of like, deep learning for radiology and for, classification of images with cats and stuff. And so, do you think that it's like that those suite of methods and techniques are going to be sort of used, or are they already being used in this area? I mean, do you think forensic examination is going to be something which is largely relegated to deep learning models in the future, or anything like that?
Yeah, I think that is a really good question. I think that examiners will be a part of the process for the foreseeable future. If for no other reason that someone needs to be able to be cross-examined in court. And that's not really something that, you know, even the best algorithm can argue for in a courtroom setting. And so I think that that's really a place where forensic science is quite weird, in that a lot of the processes are kind of driven by this end goal of a court case and a criminal case. And the other thing I'll say is that I really have no idea what the underlying, you know, database search or image processing, any sort of matching algorithm is, and that is because it's all hidden. So the FBI's algorithms is totally proprietary. I don't even think we know who designed it. And then the other thing I'll say is that it's a quite hard problem to do research on, because you know, by nature, fingerprints are identifiable. And so it's quite hard to get access to any sort of database where, you know, a researcher could try to train a better model or try to evaluate an existing model. And so I wish I had more answers for you. But I do think that, I mean, my hope is that the algorithms are getting better, probably using a lot of deep learning. But we just really have no idea kind of what's going on under the hood.
Okay, well, it looks like we are right at time. So I'd like to thank you again on behalf of everybody for a wonderful talk. It's super interesting, so I'll clap again. But this represents everybody who was here. So thank you so much, and thanks to everybody for attending. We have more seminars on the schedule, so hope to see you again. Thank you so much, Amanda.
Yep, thank you all for your time.